Hello, my friends, and welcome back to another exciting module here in BET 160, also known as Introduction to Geographic Information Systems, where we want to be able to take a look at the world around us, but see it in its most geospatial sense. And how is it organized, and what the ebbs and flows of data it actually looks like on the screen. So this week's module, we are going to continue to take a look at some of the more important foundations of GIS, where geospatial data comes from, how it's created, and really how is it organized? And how do we determine whether it is trustworthy enough to use? And also address some of the biggest misconceptions about GIS. One of the biggest ones that I can think of off the top of my head is how that GIS is always assumed that maps simply exist online, waiting to be downloaded. But in reality, every data set used by a GIS platform has an origin behind it, a purpose, a scale, and limitations. Understanding these factors is what really separates someone who can click tools from someone who can truly think spatially. And that's the main goal of our class. And so I want to welcome you to this new module as part of our weekly welcome slash module introduction. But we need to begin with where GIS data actually comes from. A major source of geospatial data is utilized through portals supported by government agencies. Organizations like the U.S. Census Bureau provides demographic boundaries, population tables, while the U.S. Geological Survey produces elevation models, hydrography layers, and topographic focused data sets. Local and county governments actually frequently publish parcel data, zoning layers, transportation networks, and infrastructure maps. So imagine this. Let's say you are studying a population density change over time. You might want to download census tract boundaries, associated population tables, join the attributes, and then also calculate the density per square mile. However, before running any analysis, we still need to be able to question that data set, be skeptical about it, and evaluate it. We have to ask questions, research-focused questions that help generate evidence to be able to support our claim as digital cartographers and GIS technicians. We have to ask questions like, what year was it created? Were the boundaries updated after redistricting? Are you comparing data collected under consistent methodologies? For an example, let's say we use a 2010 census data to represent a 2026 population, where conditions could lead to inaccurate conclusions if we are misusing data sets. And so we want to be able to learn on how to locate data, being the first step in our learning journey in this module, and then evaluating its temporal relevance and scale as it relates to our research questions and tutorials for them. When we take a look at data sets, another major source of GIS data is being collected by using technology, most importantly, remote sensing and digital imagery. Satellite platforms such as Landsat 8 collects imagery that can be used to analyze land cover, vegetation health, and urban expansion, but also helps us better understand and model environmental change. Perfect for those that want to study conservation science, environmental science, or even agriculture. Aerial orthophotos and drone imagery offer even higher resolution views of the local landscape. Suppose you're analyzing urban growth patterns. You might compare imagery from 2000 with imagery from 2026 to identify newly developed areas within a region. However, the resolution of your imagery dramatically affects your interpretation, and we need to be aware of that. For an example, a 30-meter resolution satellite may be sufficient for identifying forest versus urban land cover, but it would not be detailed enough to digitize individual buildings accurately or vegetation types. Resolution, projection, atmospheric conditions, and acquisition date all influence how useful our imagery will actually be, and that the data itself is not inherently good or bad. It's either appropriate or inappropriate for our specific purposes. And in some cases, GIS data is collected directly from the field. Nowadays, we tend to use this remote sensing, but if you need a boots on the ground approach, we'll sometimes take little handheld GPS units to, say, map tree locations in a biodiversity study, survey sidewalk accessibility for urban planning, or document invasive species presence or absence. Field data collection introduces really just another layer of evaluation, positional accuracy. A handheld GPS unit has about 5 meters worth of accuracy and may be sufficient for mapping vegetation zones, but it may not meet the standards required for broader engineering projects or property boundary mapping. And so we have to use these techniques in tandem because they're data focused, and accuracy must always be evaluated in relation to the purpose. That's going to be our big theme in this module because a data set that is perfectly acceptable for one type of research question may be insufficient for others. But what about how is a GIS project actually structured? And this is where the topic of organization comes into play, because this is where many GIS projects succeed or fail. Organization in GIS is not about tidy folders. It's about creating a logical structure that supports processing and analysis, a digital ecosystem, as I like to call it. You see, beginners often download shape files, rename them inconsistently, and then move them between folders and accidentally break data connections. I myself, back when I first started this field of study, I did the same thing in my classes. You may also be currently doing the same thing. And so we need to be aware of our actions. GIS software actually relies on structured file paths and maintained relationships. Then those relationships are disputed. Tools will fail. Projections mismatch. And that is why we have to use what they call a geodatabase. A geodatabase serves as a structured container that stores feature classes, raster data sets, tables, relationship classes, all into one managed environment. Instead of loose shape files scattered across different directories, everything will live in a centralized system designed to give you a spatial, efficient workflow. Consider wildfire risk assessment and management projects. Within a geodatabase, you might want to organize vegetation layers, slope and elevation rasters, road networks, parcel boundaries, and fire station locations. Yet behind that, each dataset contains geometry and associated attribute tables. And because they reside within the same structured ecosystem, coordinate consistency and naming conventions are easier to maintain. But beyond that, the geodatabase itself, the project files such as ArcGIS Pro project files that we are typically using in this class, acts as the command center for your workflow. The project file does not actually store the raw data. It instead just stores the references to data sets, map layouts, symbology, processing history, and tool configurations. A well-structured project might include clearly labeled maps such as raw data, processing, and final analysis, but also outputs from tools like buffer, clip, intersect, or spatial join. And these should be directed intentionally into the designated processing geodatabase. Intermediate outputs should be separated from the final publication ready layers, which would be the equivalent of your submissions on assignments. And this structure improves reproducibility and transparency. Say someone opens up your project file, they should immediately understand how your workflow is structured, if it's organized or not, because organization, therefore, supports processing efficiency, error reduction, and professional accountability. Skill sets that are very important for those that may want to transition these skill sets into a paying position within the GIS workforce. Another critical component of this module is really just creating your own spatial data through digitizing. Digitizing involves tracing real-world features from imagery or maps to create a new vector layer. Imagine you're, say, studying access to what we call a green space in a city. A green space is kind of like a park that you typically find in your city, where they try to keep it as wild as possible because of all the different resources available that the general public can use. But when you map and digitize a feature like this, you open a high resolution aerial imagery and you can create polygon features called, in this case, we're going to call it a park because that's really what most of these are. But we can manually trace the boundaries of each of the defined parks visible within the imagery. You're essentially converting, but however, digitizing requires judgment. If you zoom in excessively and trace every minor irregularity, your dataset becomes unnecessarily complex. If you zoom out too far, you're oversimplifying the boundaries. And again, scale affects accuracy. And digitizing requires intentional decisions about the level of detail that we want to use as part of our scientific communication. And that we can fact check this level of detail using what we call georeferencing, because it builds on the idea of alignment and accuracy. Now, suppose you are scanning in historical maps. That's what I do when I am trying to, say, locate a old archaeological or paleontological dig site that is no longer functioning. And in this case, let's take a map from, say, 1950s, and it only exists as a very rough image in a museum collection. In this image, it contains no coordinate information, so it cannot be aligned automatically with modern data sets by changing the projection or the datum. Through georeferencing, you can actually identify control points such as roads, intersections that still may exist today, and match them to known coordinates in your GIS environment. The software actually applies a mathematical transformation to align the image with real-world space. If control points are poorly selected or unevenly distributed, the image may distort and lead to spatial inaccuracies. In projects such as floodplain mapping, we see this. Wildfire modeling does it too, or even zonal analysis. Small alignment errors inherently influence decisions. And again, the name of the game here is that our data has to be accurate, and accuracy in GIS is not simply a technical precision. It has a real-world consequence to it. And we need to keep that in the back of our mind as we work on the material this week. By the end of this module, you should really feel confident locating reliable GIS data, evaluating its quality and limitations, organizing it within a structured geodatabase, or at least being able to connect to those geodatabases, and be able to utilize and structure project files, creating your own spatial features through digitizing, georeferencing imagery, and being accurate about it. Understanding the conceptual accuracy and by using attribute tables to answer meaningful research questions, dealing with spatial analysis. These are not isolated technical tasks. They form the core habits that any professional GIS practitioner, technician, analyst, professional needs to utilize before they enter the workforce. So if you take a central idea from this module, let it be this, that maps are constructed representations of reality. They're built upon data that was collected for very specific purposes, structured within organized systems, processed through analytical tools, and interpreted by us as humans as a way to make decisions. Your responsibility is not just to operate the software, but to think critically about the origin, structure, accuracy, and implications of your data that you use. That mindset is what will transform you from someone who's just pushing buttons to someone who actually will be able to apply technical skills into learning more about spatial relationships and grow their expertise and allow you to seamlessly transition into the workforce upon completion of study in this course. As always, if you have any questions about the material in this module, please reach out. You can get a hold of me through video chat, you can swing by my office, or send me an email. I love to talk to you about data and relationships and how can we learn more about the world around us just by looking at some attribute tables or building some polygons and seeing how they interact on the map. Once again, the material that you cover in these modules is focused around the technical aspects and tutorials found within the assignments. Thank you and have an excellent time here in Module 2.